Okay, so year 2 differentiation. Let's have a look at this chapter. So this chapter is more focused on the how rather than the why. So in year 1, you learn some of the applications of differentiation, which is to identify maxima and minima. It might be to solve problems related to tangents, for example, that share the same gradient, and so on. But we only learn sort of basic expressions such as this, how to differentiate. If you remember, we brought the power down and then we decreased it by 1. So how do we differentiate with more complex terms and functions like sine or natural log, exponentials? What about with parametric situations, not just x and y, but with t as well? Okay. Well, what we need to do is we need to have a look at a bunch of rules, basically, for how we can deal with these situations, some standard results that we need to learn and be able to prove, as well as implicit differentiation, which again is a sort of like another rule, and rates of change. This is covered more really in integration near the very end of the course. So let's start by talking about how we could differentiate sine with respect to x. So the answer is actually cos x. But why is this true? Well, let's have a look together. So if we say that we have a function of x sine, and we examine by first principles how we would differentiate it. First principles, that was when we were talking about triangles, triangles with the difference in y divided by the difference in x. We can do the same thing for more complex things like sine. So imagine this was x, and this was x plus h, where h is sort of a small increase. Well, x would give you the output of f of x. So your xy can be written as x f of x. And then for your other one, when you put x plus h in, perhaps unsurprisingly, you'll get f of x plus h out. Okay? We said that this is how to find the difference in y over x, and that we will make this gap as small as possible to get a more and more accurate answer. So this is in your formula booklet, and this is a bit of revision from year 1 differentiation. We say the difference in y's over the difference in x, well, the gap is the x difference, which is h, and we'll look at what happens as we make h smaller and smaller and smaller. Now, at the very beginning, we can't do anything because we don't want to be divided by 0. So what we'll do instead is we'll plug in these values. So sine of x plus h, like this is like the bigger y value minus the smaller y value, if you like. That's one way you can think of it, over the difference. Okay, well, now we know the addition formula. So sine of x plus h, I'd encourage you to think about what you could turn that into, sine of x plus h. Well, it's sine A cos B plus sine B cos A, or written like this, okay? Now, what else can we do? Well, one trick that we can do is we can break it up into a few parts. So I think I'm just going to go off to the side here. From the numerator, I'm going to factorize out sine of x. If I factorize out sine of x, I would get cos h minus 1, okay? And for the other one, I'm going to factorize out all of the terms that have cos x in them. What has cos x in it? Well, it's just sine h, okay? This is the numerator. Another thing I'm going to do is I'm going to break up the denominator to be like this. Just verify that this does work by adding fractions backwards. And then I'm going to do another trick. I'm actually going to write this as cos h minus 1 over h multiplied by sine x. If you multiply fractions, that would take you back. Okay, you could do the same. So that's that one there. You could do the same for this other one over here. So you could sort of break it up, attach the h to the sine h only. As long as it was multiplied by cos of x, that would take you back, wouldn't it? So that's how we get this line of working out here. Okay, so we can use the addition formula, some clever sort of factorizing, a few tricks with rewriting fractions. Well, what are we going to do with this one now? Well, as we've learned some small angle approximation, we can take this further. So you probably don't need to go through quite as much detail, but what happens to sine h, for example, as, or sine x more generally, as x gets very small, it becomes closer and closer to the thing itself. So sine h is about h. So in other words, this is a bit like h over h, which is 1, which would leave you with cos x. You can use that as a guide if you know what the result should be. So what happens over here? Because it seems like the sine part should disappear, but why should it? Well, cos of h is the same as what? Well, it's about the same as 1 minus h squared over 2, or something equivalent. Then you've got your minus 1, and then you've got your divided by h. Things will cancel, but they won't cancel enough. You'll be left with an h here, and as that approaches 0, it means that for the whole left-hand side part here, it's going to disappear because you're sort of multiplying by 0. Whereas on the right-hand side, you effectively have like 1 cos x, or just cos x. So as you actually put the limit into practice, right at the end here now, you'll be left with sort of this here, and you'll actually get left with cos x. So that's what happens when you do it by first principles. In terms of what you need to be showing as you're working out, this would sort of be the first key line of working out. You need to show these steps here, this step here. So lots of mark schemes, I haven't seen it explicitly referred to that you must go through the steps of small angular approximation. It's probably adequate if you just, where are we? If we talk about each part. So if we say that this leads to 1 and that the other part leads to 0, I think that would be satisfactory. Okay, and the final answer of cos x. That's what we need to be able to show. So this is a proof that you will be asked to do. It's very similar for differentiating cos and things like that also. So it's only worked when we use radians, because one thing we talked about is that if we compared radians and degrees, our approximations worked very well for small numbers with radians, but they diverge quite significantly with degrees. So the importance of this is any time that you differentiate or integrate with trigonometry, you need to be in the radians mode on your calculator, okay? Whether it tells you this explicitly in the question or not, this is something that you must do, and it's sort of expected that you know what to do with that. So now that we've proved it, the results, and I mean, I think it's one of the questions in the book, I would encourage you to have a go proving for yourself with cos. They follow this sort of cycle. Sine goes to cos, and then cos goes back to minus sine. Well, any numbers at the front don't make a difference, so sine goes to cos again, or in this case, minus sine goes to minus cos. So the red way round, the red part shows you differentiation. Later on for chapter 11, when we do integration, you'll be expected to go the other way round. The antiderivative is the blue, okay? So this is how I sort of remember it in my head as a cycle. What about expressions like this, where there's a number in front of the x? Well, for now, we're just going to learn this as a pattern, but this will be proved later. So this isn't its own rule. It's a result that we will use for later. So what we do is we keep the input the same, like we did with e, for example. The sine bit becomes a cos, okay, but then we need this number at the front as well, okay? So you'll multiply it by k as well. So let's do this next one. Cos becomes minus sine of the same input, but it will also be multiplied by that k as well. So we will get this kind of result. So this is linked to something called the chain rule. We haven't done that yet. We'll do that later. Let's just do some quick fire questions. So sine goes to cos of the same input, and you multiply by the constant that's in front of the x. So that's a 3. Okay. Pause the video, have a quick think about these ones here, and then just check them as I reveal them. Okay, so hopefully there should be no big surprises. If there's already a number there, that's fine. Just multiply the numbers together, like we did with other kinds of differentiation. Okay, careful with fractions. So here, the minus 2/3 gets multiplied by a half, so 2 over 6 becomes a third. There's also a sign change from minus cos to sine. And what are the implications? Well, it lets you solve questions like this on the board. So a curve has this equation. So I don't know what it looks like. Let's just pretend it looks something like this. Find the stationary points. Well, stationary points, and it does say points with an S, so there should be more than one. That's when the gradient is equal to 0. So I need to start with this function, and I need to differentiate it so that I can set it equal to 0. So dy dx equals, sorry, that's just a half. So you might have some year 12 type differentiation chucked in as well. Minus cos turns to sine. So plus sine 2x. What mistake have I made there? What have I forgotten to do? That's right. If it's kx, you need that k at the front as well. Okay. We set it equal to 0, and we start to take things to the other side. So minus a half, then divide that by 2. So minus a quarter equals sine 2x. Okay. If you do arc sine of both sides, minus a quarter, you'll need to use the radians mode on your calculator, won't you? Okay, so is my calculator in that mode? Yes, it is. So if I do arc sine of minus a quarter, I get, I'm running out of space, but let's do something like this. I will get arc sine, remember, means that will be 2x. So it'll be equal to minus 0.25. Is it minus a quarter? Yes, minus 0.25. I think we'll have a look at the answer just because I'm running out of steps. But what you would need to do is you need to make sure that this fell within the domain that's being talked about, which currently it isn't because it's a negative number. So we need to add on and so on. And we need to use symmetries here before dividing both answers by 2. Let's have a look actually with a slightly neater bit of working out. So there we go. We get this one here. This is the value that the calculator gave me to start with. But the problem with this is it's not in this part here. So a good way to fix it straight away is to add on 2 pi. That would be a good first step. So if we add on 2 pi, what does that give us? It gives us this value here. Okay, it gives us your 6.03 blah 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 blah. How could we get the other value? Well, what are the rules about sine? The rule about sine is that if you want sine of an angle, what you can do is you can do 180 minus the other one. Okay, so this symmetry is discussed in this rule here. Because it's radians, though, it needs to be pi. So to get the other value, we could do pi minus 0.257, which should give you your other value. So I'm just going to take that. Yeah, I get this value here as well. Now, why am I going with these two values when 6 is clearly bigger than 3.14? Well, remember, as soon as you do your arc sine, as soon as you undo the sine, that leaves you with this part here. And you'll need to adjust this at the end. But as soon as you do your arc sine, that's when you do your symmetries and you find all your values and things. It takes place immediately after you use your arc sine. So we get these values here. We know the negative is no good because it doesn't fall in there. But what we do is we divide both of these by 2, okay? And then we find that they are, in fact, inside that range there. These are your two x values. Plug your x values back into the original equation to get your corresponding y values and make sure that they clearly link to each other. Right, now we've done that then, have a go at this question here on the board. So remember, radians mode on your calculator, differentiate, turning points are set equal to 0, and think very carefully about picking out all of the values that solve the equation before you do any final steps, like dividing by 3, okay? Dividing by 3 is the very last step. So I'm assuming that you've done that. Let's take a look. So differentiate set equal to 0. Get the trig bit on its own is really important. Okay, do your arc cos on both sides. And when you get this value, use your symmetries here. So if I get this value to get to the other one, what's the rule about cos? The rule about cos is it's 360 minus the other one. For radians, it's 2 pi. So if you do 2 pi minus your answer, you will get this other one here. The dividing by 3 is the final step, okay? Well, it's not the final step. You need to find your y values, of course, as well. But for the difficult part, finding your dividing by 3 comes at the end. That's a very common mistake that people make. And that should let you access 9A.